This presentation will also be recorded for future viewing. Okay, Corey, can you see that?
Yes, I can.
All right. Okay, well, should we get going? Today it's January 19th. You're presenting on the Water Reclamation Plant Facilities Plan. This is the public hearing for that plan for comment. And today, Harold Volth, Don Esping, Matt Baker, myself, it's Matt Baker, and Corey Bjornberg will be presenting on this presentation. With that, I'll hand it over to Corey, I believe.
Thanks, Matt. Why don't we go ahead to the next slide? So we're meeting today to discuss the Rochester Water Reclamation Plan, our treatment needs, and the overview of the facilities plan created by Brown and Caldwell. So the primary issues that we had to address for the facility plan was some permanent limit changes, primarily a reduction in our phosphorus load of about 15%, as well as our HPO plant, which was built in the early 1980s, is 40 years old, treats about 75% of our flow, and is needing an upgrade. So Brown and Caldwell was hired to prepare the facilities plan, which resulted in a three-phased approach to address these issues. Phase 1 was the remodel and effluent upgrade. Phase 2 was the liquid treatment upgrade, and Phase 3 was a solids treatment upgrade. So we'll discuss those more in detail in the following slides. Next slide, please. So the Rochester Water Reclamation Plan is located on the north side of Rochester. The address is there, and you can see a site layout. And we discharge to the South Fork of the Zumbro River. Next slide, please. The primary goal of the water reclamation plant is to protect human health. Secondary goal is to protect the environment. So we want to make sure our effluent quality meets the state's requirements to protect aquatic life downstream of the treatment plant. We treat about 14 million gallons a day, 24/7 operations since 1926. The 1926 plant is actually at a different location, but we've been on the same site for about since the early 50s. And we've gone through a series of upgrades that you can see in the pictures here. Next slide. Just a big picture overview of wastewater. Obviously, we collect wastewater from the Rochester citizens. It travels here through a series of sewer pipes, at which point we treat it, and the treated effluents discharge the river. But there's also stabilized biosolids that are produced and given away free to farmers in the area. There's also several resources that we collect. Methane is used in boilers and generators to produce some of our own heat and electricity. Since 2013, we've been spending a lot of time trying to optimize our facility. We've seen reductions in electricity, water, natural gas, and chemicals through that time period. Part of the goal of the facility plan long-term was to do even more. So that weighed heavily in our decision on the direction we took. So. Next slide, please. A quick overview of the Rochester plant. The green area is the headworks. We have fine screens, grit removal, and equalization. From there, flow is split to one of two plants. The HPO plant, which is the larger plant, treats about 70% of our flow. It consists of primary clarifiers, first stage removal for BOD, second stage removal for nitrification. The smaller plant is a conventional air plant and treats about 30% of our flow. I should state that the HPO plant does use a cryogenic air plant that we generate our own oxygen on site. We do have gravity belt thickeners, both for our WAS as well as our digested sludge, and then we have anaerobic digesters for our solid stabilization. We do have boilers and a cogeneration system on site to produce our own heat and electricity, as well as a couple solid storage tanks to hold our stabilized biosolids until we can apply them either in the spring or fall. And then finally, we have a disinfection system and then a dechlorination system to treat before we discharge the Zumbro River. Next slide, please. To give a little background on how the facility plan came about, in 2015, we were approached by the MPCA about reductions in our current limits. With the concerns regarding both reduced limits and the aging HPO plant, we decided to proceed with a facility plan. We got council approval in 2017. Brown and Caldwell was selected to do this work, and through the next 2 years, they completed the facility plan. In 2019, we came up with the phased project approach to address all the issues, and it was brought forth to council. In 2019, phase one was approved to go out for bid. In 2020, we started that work, and also in 2020, we're finalizing our permit negotiations with the PCA, and in 2021, we're going to start seeking low interest loans and grants for phase two. Our hope is to start phase two engineering and constructions in years 2021 through 2024, and then phase three will occur in the late 2020s. Next slide.
So I'll take it from here. This is Harold Voth. So the facilities plan, as you see the goal there, comply with new limits. And that is, as Corey mentioned earlier, based on anticipation of more stringent phosphorus limits. And not only to meet future regulatory limits, but also to ensure sufficient capacity for future growth in the Rochester service area. The plan also not only considered the cost of new construction, but also the total life cycle cost of operating and maintaining the facilities over the life of the project. Key goals, as you see there, A through E: reduce energy demand. The plant has consistently been lowering their chemical and energy consumption, but want to continue along that trajectory. Clean design. What that means is to simply simplify the plant. There have been 6 major expansions since the 1952 construction, and those expansions have brought levels of complexity to the plant that they would like to reduce for future operation. And again, with that simplicity comes a decrease in maintenance costs. The plan wanted to consider innovative processes. These would be the best available technologies to meet the treatment and process requirements. And not just new, but the best proven technologies. These aren't accepting unproven, but those that have been demonstrated to be effective and yet take advantage of the best available science and engineering. And then long-term holistic approach. Again, to look at the plant in total, and to provide not only flexibility to deal with changing influent characteristics, but also the flexibility to adapt to future regulatory requirements in the long term. And then the different components of the facility plan, as you see, started with a rigorous characterization of the existing wastewater coming into the plant, looking at long-term growth projections, looking at permit requirements, and then looking at both liquid and solid stream, looking at the methane gas production and how best to optimize and take advantage of that energy source. Look at the industrial component. There's a significant industrial component coming into the city of Rochester, but there's some variabilities there. And how does the plant adapt to either changes in those contributions, either additional industries coming in or those actually closing, shutting down. And then, as we've talked about, efficiency. Try to not only optimize as efficient as possible, but also to gain efficiency in terms of energy recovery and effective use of the methane produced by the treatment process. Next slide, please. Here's a high-level overview of the plan. Again, I'm looking at long-term flows and loads going out to 2045. The flow is are the gallons per day coming into the plant. The loads are what makes up the wastewater. What are the constituents in the wastewater that need to be treated? And what are those projections to make sure that the new facilities will adequately meet those treatment requirements over the next 25 years? Looking at the range of effluent limits, Don will talk about that in a minute, how we looked at the different regulatory scenarios. We implemented or took advantage of both hydraulic and process modeling. Hydraulics, again, that's the flow coming into the plant. Modeling to make sure that the gallons coming in can pass through all of the treatment processes without any spills or backups, that we have capacity. And then process modeling to ensure that the processes can meet the treatment objectives. I looked at 3 different treatment pathways. Again, Don will get into the details of those. Similarly, looked at the different solids treatment alternatives, and again, looked at reuse and energy recovery systems to, again, take advantage of any potential energy savings with the project. Next slide. And then, as we indicated, starting out by looking at the flows and loads that are dictated by the growth in the Rochester area. There was an assumption of a 1% annual growth, and which leads to again, in 2024, the planning window, ultimate treatment capacity of 19.9 million gallons per day compared to the 14 million gallons that the current rated capacity of the plant. And then the flow and loading projections use the conventional criteria established by the Minnesota Pollution Control Agency. And so again, in the table there, you see a variety of numbers. There are the annual average values, but there are fluctuations in those flow values, and there are peak values that must be taken into consideration, so that if you have an annual average of, as indicated in the table there, of say currently 12.9 MGD, under wet weather conditions, those flows can spike up to, as indicated, they're up to 34, 39 million gallons a day. And so the capacity of the plant needs to be designed to accommodate those flows. Next slide, and I'll turn it over to Don Esping to talk a little more then about the actual treatment alternatives that were evaluated.
Hey, thanks, Harold. This is Don Esping. And first thing I wanted to talk about is a little bit about the effluent water quality goals for the planning level. We looked at 4 different treatment levels, if you will. And essentially, treatment level 1 was the existing permit with some reductions in the total phosphorus discharge requirements in terms of meeting a monthly average of 0.8 milligrams per liter of phosphorus per liter. And then as we get into levels 2, 2X, and 3, we added effluent criteria for total nitrogen in terms of as total nitrogen or as nitrate and nitrite nitrogen in terms of levels 2 and 2X, and also reducing monthly phosphorus discharges instead of 0.8 going down to 0.4, And then finally, looking at level 3, you can see that our annual nitrogen further decreased down to 4 milligrams per liter with a total phosphorus of 0.1 milligrams per liter. So it just kind of gives you a range from a planning perspective of current and potential future limits that we wanted to evaluate facility requirements for in the planning period identified. Our first step in terms of our facility evaluation was a screening process where we looked at 19 different alternatives. The alternatives varied widely in terms of being very conventional treatment technologies for nitrogen and phosphorus removal to more innovative approaches, getting towards reducing energy at the plant or minimizing the footprint in facilities at the plant and so forth. But essentially, we looked at all these alternatives and we evaluated them based on the criteria that Harold had mentioned previously. And from that, we came away with 3 main treatment pathways for further evaluation. If you go to the next slide. Here are those 3 treatment pathways. Pathway 1 maintained the current parallel systems, if you will. And you can see with that pathway 1, there's a treatment level 1, which then feeds into treatment level 2 below it, which feeds into treatment level 3. And treatment level 2X isn't shown here just for simplicity. And then similarly with pathway 2, here, instead of maintaining parallel systems with HPO, high purity oxygen activated sludge, or HPO, and air activated sludge, here is converting the entire plant to air activated sludge, BNR, or biological nutrient removal. And then pathway 3 is going with a more innovative approach of converting the entire plant to aerobic granular sludge. So with that, we can go to the next slide. So what we wanted to do quickly is just walk through each of the different pathways and level treatment levels, if you will, and what that might look like for the plant. We'll see a lot of these flow schematics as we're showing here. But essentially what this plant is showing, or this schematic is showing the existing plant liquid stream downstream of the existing grid system. And what you can see on the top line is existing HPO train, which is primary clarifiers with ferric chloride or FeCl3 added to promote solid separation and diversion of carbon to the digesters to produce digester gas or energy. And then following that, there's 2 activated sludge plants that are identified by a reactor that's mixed with high purity oxygen, followed by a clarifier and solids being recycled. But the whole idea here with pathway 1, level 1, is we noticed that we could maximize capacity again for carbon diversion to the digesters, and also just to minimize existing or the additional facility requirements if we fully utilize the treatment capacity in that HPO train. And you can see some of the assumptions there, but really the kind of some of the key things were increasing a couple of the mixers within the HPO train so that we can transfer enough oxygen, and then diverting some of the flow around first stage to second stage HPO to maximize capacity of that system. So if you go to the next slide, you'll kind of see this is what it looks like in terms of the new systems for level 1 with the parallel pathway 1. There's you can see within the existing HPO train, there's a couple of highlighted arrows, but mainly it's replacing the existing cryogenic facility with a new vapor swing adsorption HPO or high purity oxygen generation plant, along with the additional mixers that I had mentioned, and then expanding what we call the ABC plant shown to the left with a new primary clarifier, a couple of new aeration tanks of similar size to the existing, and then a new final clarifier. As we go to treatment level 2 and 3, the whole concept here, again, we're going for treatment level 2, we're going to a TN of 10 and a total phosphorus discharge of 0.4. And then effluent for level 3, we're going to a TN of 4 and the effluent concentration of 0.1 milligrams per liter. The concept here was to maximize the HPO train capacity to generate or maximize carbon diversion to the digesters to maximize energy production, and so forth. So you can see the ferric chloride addition still to the primary clarifiers. Then you'll notice there's a little bit of a change in the flow schematic. We still have a high purity oxygen first stage, but the second stage, in order to get nitrogen reduction to the levels that we wanted, had to be converted to air activated sludge. Because there's less carbon coming into this system, since we're moving it up front, we went with a more innovative simultaneous nitrification, denitrification, or low DO system to maximize TN removal for the amount of carbon available. So you can see the flow scheme there gets a little bit more complex. And then on the bottom, you'll see this is the ABC train, where we have converted to a 5-stage BNR with an anaerobic zone as they currently have, but then adding an anoxic zone, mixed liquor recycle, and a subsequent anoxic zone to that flow scheme. When we get to level 3, because of the low nitrogen requirements, we do need to add supplemental carbon and expand filtration. Level 2 requirements for any of the options requires filtration just to get down to monthly concentrations less than 0.4 milligrams per liter. With that, we'll continue moving forward. And what this chart figure here is showing is kind of more of the facility requirements based on the different levels. So we kind of identified on level 1 what was required, and that's shown in red. And then you can see as we get to level 2, which is again the TN of 10 and a total discharge or phosphorus discharge of 0.4, or the additional facilities are shown in light blue. And then we get into level 3, we have a further expansion of the filtration system, along with adding additional carbon for total nitrogen removal. Okay, and then one of the twists in terms of pathway 1 was what we called treatment level 2X, and this is where we're reducing the effluent nitrogen in terms of nitrite plus nitrate to 10 milligrams per liter. So not quite as stringent as a TN of 10, but here we could actually use the existing system and convert the HPO train into an A2O process, where we have an anaerobic selector and an anoxic zone, and then along with the mixed liquor recycle, using high purity oxygen, provided the last cell, additional cell in that HPO train is air activated sludge. And then similarly down below in the ABC train, you can see that we're running a 3-stage system with an anaerobic zone and an anoxic zone and an aerobic zone in our system. And this is just simply what the train, that conversion would look like. So it's a little bit different compared to the other pathway 1 options in terms of we're using existing tankage. In this case, you can see in purple that we're using the existing 1st-stage HPO reactors as anaerobic selectors or for denitrification or return sludge. And then we're using some old aeration basins as anoxic zones within that train. They're shown in light blue. And then in green, we've got the HPO aeration tanks with some slightly larger mixers for oxygen transfer, but then adding a 4-cell with fine pore diffusers to help with nitrification in that system. And then an expansion of the ABC train shown to the lower left with 2 new clarifiers shown in red, and an expansion of the main bioreactors shown in yellow. Okay, moving on to pathway 2 in terms of level 1. Again, this is where we're meeting monthly discharges of 0.8 milligrams per liter as phosphorus. And the concept here with the conversion of pathway 2 is to really simplify the process, and we can do that by operating as a single plant concept. So no longer running 3 individual activated sludge plants, but operating 1. And we can do that by combining all the return sludge before it's moved up into the bioreactors, as shown here in the flow diagram, and then also combining the primary effluent and then feeding that into the bioreactors themselves. So very simple concept, minimizes tankage and eases or simplifies operations significantly. And this is simply what it looks like. You can see the main components are listed on the left. There's the new RAS and primary effluent distribution boxes, where everything is combined and then distributed to the aeration tanks. And then you can see the HPO train to the right. We're reusing tankage wherever possible. So we're converting, again, those first stage reactors to anaerobic selectors, converting the second stage HPO reactors to aerated bioreactors by installing fine pore diffusers, and then expanding that system with the additional force cell, and then expanding the ABC train by adding 3 new aeration tanks to that train itself. And similarly, this is what alternative 2 or pathway 2 with level 2 and 3 looks like. Here we had to go to 5-stage BNR simply because of the amount of non-biodegradable nitrogen in the plant influent. Typically, we could use a 3-stage system. But essentially, it's a very similar concept. We're running a single plant, and we've just added to the anaerobic zone and aerobic zone, we've added the 2 anoxic zones to this configuration for nitrogen reduction, along with filtration for further reduced phosphorus reduction. For level 3, we need to add supplemental carbon and expand filtration to meet the discharge requirements for that system. All right, and here's what it looks like in terms of systems. You can see the level 1 facilities that we talked about earlier, shown in blue, or shown in red, and the level 2 facilities to get to a TN of 10 are shown in light blue. And then as we go to level 3, or the most stringent facility requirements, we have the additional facilities shown in purple. In terms of pathway 2 with treatment level 2X, again, this is an A2O process. So here we can simplify our flow scheme a little bit, and just having a single anaerobic, anoxic, and aerobic zone with a mixed liquor recycle. And if you go to the next slide, it kind of shows an overall layout of what that might look like. So very similar to alternative 2, just simply not, the tankage is actually the same. It's just one has a second denitrification zone where this one does not. Pathway 3 was converting to aerobic granular sludge. And the basis for our analysis was on the Aqua and Areta aerobic granular sludge system. And it's shown here. And essentially what we're doing is, instead of having each of these individual zones for dedicated anaerobic zone, a dedicated anoxic zone, dedicated aerobic zone, we can do that similar treatment in a granular, in which the diffusion into the granule, you can get the same micro environments as you would in the macro environments in the previous alternatives are summarized to get the same level of treatments. So we did look at pathway 3, or the AGS system, for levels 2 and 3. Again, looking at TN of 10, 4, and phosphorus of 0.4 and 1. This is just a simple schematic of an AGS system. What you'll notice different here compared to the previous schematics is we have an EQ tank up front of the primary clarifiers, or what's designated as PC. That's because the peak flow capacity of an AGS system is less than the other alternatives where we need additional EQ. And then there's some additional tankage that we haven't identified in terms of water correction tanks or sludge buffering tanks that we'll kind of show in the next schematic. So the whole concept here with the AGS system, luckily, is we could utilize the tanks that are existing for the AGS tanks. Typically, the AGS bioreactors need a minimum sidewater depth of 18 feet, and with the existing plant, there's plenty of tanks that had that sidewater depth capacity, so we could do that. So what you'll see here is there's numerous tanks, but essentially we need 8 AGS reactors, as we'll call them, at 1.5 million gallons apiece. So we can use 5 of the final clarifiers to do that. We can convert one of the aeration ABC complex aeration basins to an AGS tank, and then also use some of the second stage HPO reactors as an AGS reactor. So it had a really nice fit in terms of facility requirements, and it left over some additional tanks for these additional tanks that we're talking about in terms of water correction level tanks or sludge buffering tanks. The existing primary clarifiers in the HPO train became supplemental flow EQ, as you can see in here. So there's a lot of facility adjustments for level 2. When we get to level 3, where we get to lower nitrogen requirements, you can see that we needed some side stream treatment to help reduce nitrogen in the side stream to meet our effluent limit, our criteria, along with expanding the effluent filters to meet the reduced phosphorus discharge requirement. In terms of life cycle costs, this is a summary of the capital costs for each alternative. The annual O&M net present value for each alternative, assuming operations begins in year 2025 through 2045, and then the overall net present value. So as you look on the first 3 rows, comparing pathway 1 and 2, the conventional BNR system has a lower capital cost, along with lower net present value. So economically, it's very attractive, along with operationally being more attractive to run 1 activated sludge plant than 3 activated sludge plants. Moving that into level 2, whether it's level 2X or level 2, again, pathway 2 has the lowest capital cost, along with lowest net present value compared to the alternatives that we looked at. And then as we get into level 3, alternative or pathway 2 has the lowest capital cost, and its net present value is slightly higher than pathway 3, which is the aerobic granular sludge. But from a planning perspective, it's within 10% and considered equal in terms of long-term net present value. This chart just shows some of the impacts of each of the different pathways in terms of some of the key criteria that were mentioned previously in terms of lower energy or clean design, decreased maintenance or innovation or what have you. You can see that essentially pathway 2 and pathway 3 had the most positive impacts, or that'd be the pluses, as you can see, where the parallel system was less attractive in terms of long-term goals for the facility plan.
Sorry. Thanks, Don. This is Nancy Andrews, and I'll be covering the solids portion of the facility planning. So basically, the solids come from 2 different streams. The first is the primary sludge, which are the solids that settle out in the beginning of the tanks, in the beginning of the treatment scheme before you get to the biological process that Don was talking about. And then there's the waste activated solids, which are the surplus biological solids that come out of the process that Don went through. So those 2 solids go to anaerobic digesters, which is the photograph shown on the left, and they're held for 20 or more days in those tanks. And biogas is created as a byproduct of that process. And as they stay in there, they break down and reduce in volume. And then the middle picture is the thickening process. So both the biological solids and the solids coming out of anaerobic digestion go through a thickener to remove some of the water. And then the picture on the right is a tanker and sludge applicator. So this is the equipment that's used to deliver kind of a slurried sludge to the farm fields for use as a fertilizer agricultural amendment. So what we were looking at for the facility plan was how does the growth in sludge production through 2045 affect all these processes? So from digestion, then the thickening, storage, solids handling, and odors. We also looked at fog, which is fats, oils, and greases, and high-strength waste. So these are outside materials. So the fog is coming from restaurant waste, essentially. And then the high-strength waste would come, for example, from food processing industries that have extra kind of food waste. So if you add that kind of alongside the other sludge streams that I was talking about, you get more digester gas, and you have more ability to make electricity from that. And then in terms of solids hauling alternatives, because the existing system is hauling a slurry, it makes it very easy to store and it's relatively easy to transport and inject. But because the solids are land applied over a period of about a month or so in the spring and the fall, there's a lot of trucks coming and going from the plant to move the solids out. So we, in addition to, alongside looking at the existing methods for land applying the solids, we looked at dewatering, which makes something that's more like a dirt-like, kind of a wet dirt consistency, and then drying, which uses either biogas or natural gas to heat the sludge and drive off all, virtually all of the water, and makes kind of a fertilizer pellet. Next slide. So as we look specifically at the digesters, the existing digestion approach is mesophilic. So it's operating at 98 degrees. So it's kind of taking advantage of the microorganisms that come out of our guts to break down the sludge. And to accommodate the future growth in sludge production, the proposal would be to use primary sludge thickening to get rid of some of the water that's carried into those digesters now. So if you have less water carried along, then the solids stay in the digesters for a longer period, and so that even if the sludge production is increasing, you can take advantage of the tankage that you already have. So you see that alternative in the right-hand column of the table at the bottom. And if you look at the life cycle cost, or the net present value on the bottom, you can see that was the lowest cost, both in terms of capital improvements, and then also life cycle costs, considering maintenance and fuel costs. The other alternatives that were looked at as possible changes in process involve thermophilic digestion. So that's like a 120-degree process, and that higher temperature speeds up the reaction, so you can do more within the existing tankage. But that higher temperature has a penalty in terms of the heat that's required and the energy input. And then a variation on that is thickening the primary sludge, so there's less sludge that needs to be heated, and that drives down the heat requirement. But regardless, the two competing alternatives ended up having a higher net present value than continuing on the current path, but adding gravity thickening for the primary sludge. And just to summarize the other solids recommendations, we looked at thickening, and somewhere out towards the end of the planning period, we foresee a another gravity thickening unit. In terms of the solid hauling options that I mentioned, dewatering and drying, the economics really favor continuing with the liquids or the slurry hauling. And the fog receiving is something that's a little, is at the discretion of the plant in terms of pursuing that. So really no major process modifications over the current operations. That there would be a cost to retrofitting an existing tank for use as a gravity thickener. Another tank would be retrofit for storage, which would act as a redundant unit to the gravity thickener. There's another tank that's kind of underused at this point that would be converted to a sludge transfer tank, and that helps reduce some of the pumping complexity for transferring sludge among processes. A fourth underused tank would be used for biosolid storage in the future. I mentioned the gravity belt thickener already. And then a second load out for biosolids land application, because there's all the liquid trucks that are going back and forth between the wastewater plant and the fields are kind of going through a single loading station now. So, and that becomes a bottleneck. So this is intended to relieve that. And then because there's methane replaced in the digesters, which is almost entirely used at this point, that if the boilers or the engines that use that go down at any time, you need to have a way to safely combust that gas as a kind of a backup or an emergency outlet. So that's actually already been replaced due to its age and safety concerns. Right, so reuse and heat recovery. So one of the assets that the plant has is water that can be reused, and then thermal energy, because the water tends to be 55 to 60 degrees. And the buildings that are being heated because of the odors that are associated with wastewater plants, they're exhausting a lot of air and running that through odor control. And the air that's being exhausted needs to be made up with fresh air coming in. So what this system does, and it's actually pretty unique in the industry, is use that 55-degree water to preheat, say, 20-degree winter air and reduce the amount of either biogas or natural gas that has to be burned in a boiler to heat the buildings. And so the issues that we were trying to address through the facility plan was that the water that's used for this heating is withdrawn from the final clarifiers, which is where the biological solids are separated from the water that's leaving the plant. And the way that system is arranged now, it's not very good in terms of trying to withdraw clean water for this system. And it also disrupts the settling of the biological sludge. So it's a disadvantage for the wastewater treatment plant. So the proposal in the facility plan is to essentially separate those two systems so that the heat recovery and the water reuse is using cleaner water, and the withdrawal system isn't disrupting the settling of the biological sludge. Next slide.
Okay, I think I'm going to take it from here. This is Matt Baker. I'm the project manager here at the Water Reclamation Plant. And to break down the facilities plan, which is a very large document, we decided to break it up into 3 phases of projects. Phase 1 is shown here. most of this is already under construction or built. The waste gas burner is already built. That's located at the furthest north, uppermost of the picture here in orange. And items 4 and 5, the remodel and storage facility, are currently under construction here at the plant. And the disinfection stage, which is the chlorination, dechlorination, and step aeration systems, are currently on hold until we have our permit as issued by the MPCA. But once that's issued, we will continue with that project, which is already designed as well. Phase 2 is the liquid treatment upgrade portion of the project. This is the largest portion. It's 54 million. This is what we will be applying for loans through the state process as well as grant funding. This is what Don talked about primarily, as well as some of the stuff that Nancy talked about regarding the liquids treatment and kind of how that ties in a little bit to the solids treatment and water reuse efficiencies that we just got done discussing. But mainly the majority of the work and cost is the liquid treatment, upgrading this system, changing it from 2-plant design of high purity oxygen and activated sludge process to a single plant design, which is the activated sludge type process. Phase 3, later 2020s. It had an original cost of 15 million. This is the work that Nancy reviewed in terms of the solids treatment. However, we've had 3 large industries close since the facility plan was completed. They accounted for a large portion of our loading, and so this project cost is going to be reduced. We also don't plan to continue to pursue the additional load out or some of the storage and some of the storage components of this project, just because those industries have left. We no longer require that additional faster loadout system or the additional storage. So that is one thing that's changed since the publication of this facilities plan. Okay, so wastewater rates, how does this impact the rate structure? The last rate study was done in 2015, and it did include several projects, and we'll kind of show a really elaborate chart next, but it does show the projects in there. It did have this planned. We did, through the facilities planning process, realize that there's actually less total capital projects further out, and so we do plan on seeing we'll still have a rate increase, but a reduction compared to what the last rate study planned. The last rate study had projected 4% annual rate increases. At least in the next 6 years, we're looking at less than that. There'll still be an increase because these projects are still required, but a smaller percent increase. We do look at affordability. Currently, we are at 0.6% of the median household income. Back in the 2015 rate study, the EPA deems it unaffordable at 2%. So we are pretty far underneath the median household income. And we do have the next rate study occurring this year. It's going to start in the next few months, and we will be presenting that in the fall of this year to City Council for approval of rates. So charges, expenditures, basically this is a very complicated chart, but it shows everything on one chart, so that's why we like to show it once in a while. But you can see the purple line is the average monthly bill for residential customers. You can see it continuing to go up, at a fair amount every year. Again, that was based on a 4% annual increase. It will be less because we've taken out some projects. An example, you can see the $54 million project in this chart in 2022 that is still occurring. And then the $16 million project in 2023, that was similar to the solids handling project that was for $15 million, the phase 3 in 2023 on here. We're going to be moving that project out further. It'll be less. Also, there's capital projects, on the chart in the kind of turquoise blue. several of those projects are no longer going to occur. Some of these are sewer system projects, but some of them are plant projects, such as the $125 million project in 2036. So that's no longer required as far as we're aware. Obviously, things change with permit requirements, but with the elimination of some of those projects, the rate increase will be less, closer to the rate of inflation. Again, some of these projects were accounted for, or all three of these phase 1, 2, and 3 were accounted for in the last rate study. Here's a summary of those project costs: $13.5 million for phase 1, $54 million for phase 2, and $15 million for phase 3. Phase 1 is near complete, and it's paid for by retained earnings or our fund balance. Phase 2 and 3 will both require state loan and financing, and we'll be pursuing that here this year with the state for phase 2. We also have an annual debt of about $9.5 million that goes through 2026. Once we are finished with 2026, all of our debt is paid off, except of course these new loans that we'll be taking out for these projects. The entire facilities plan is located online at rochestermn.gov/wastewater. All the ordinances for the city sewer ordinances are online as well. Again, on the city's website, rochestermn.gov, and they can look there for sewer rates. Also, our rates are posted online on the same website as well, in case there are any interest in rates. Again, this is a brief aerial view of our facility. It's located at 301 37th Street Northwest in Rochester, Minnesota, zip code 55901. The flows that were used, and we did use the Minnesota Pollution Control Agency guidance guidelines sheets for flow projections for peak flow, and we did use the Rochester Destination Medical Center documents for projected growth, which was 1.5%. If there's any comments, please address them to myself at mabaker@rochestermn.gov. Phone number is 328-2652 if there are any questions. We do have comments due fairly soon. We are bringing this to council tomorrow for approval, but we won't be sending this to the MPCA for at least 10 days from today, just to make sure we capture all comments and information needed. So I think everyone on the call has had a chance to talk once, except Wendy. Wendy, do you have a joke or anything?
No, I think I'm good. I mean, poor Eric. I'm hoping if you have questions, I'm bummed we don't have more people here because I think it's a great topic. But if you have questions, please feel free to ask them. And otherwise, we can certainly, or if you think of them later, certainly feel free to email them to Matt.
Yeah, I appreciate it. I'm glad I could help be part of an audience so you weren't talking to the same crew as always. I know how it goes. The one thought that kind of caught my eye was that growth that you just mentioned at the end here. With the lack of industries kind of dropping out, is that realistic, or was that kind of a thought process, or was it the expectation that they might come back, so we'll just keep that capacity?
We've actually looked at that since this facilities plan. We're publishing it the way it is, but we are looking at with the industries gone, and then continuing that 1.5% growth, because the town with DMC is still going to grow with residential growth and some general commercial, but the loading is definitely going to be kind of dropped for the industrial growth portion. We do also have another industry in town that has grown significantly in recent years, and is actually that was a smaller industry, has now surpassed some of those that have left. So they are taking up a large portion of our load as well. Well, if there's not any other questions, I guess that's all we have today. And thanks, Eric, for attending. We appreciate it. Okay, I think with that, that's the end of the presentation.
Thank you, Matt.
Yeah, thank you
Thank you.
guys
Yeah.
for attending
Thanks,
and presenting.
everybody.
Thanks, everyone.